This is Sonja Philipp from Germany. This is the fifth live video of a series on geology for the future that I give this week. I'm just checking here. It looks like that I am live on Facebook. If you see that, feel free to invite your friends or colleagues. I'm also happy if you share in the comments where you are watching from, and if you are a professional geologist or a geology student or just interested. I see Christina is here again. Nice to see you again, Christina. Good evening to you too, and to everybody else. Of course, I see there are some people watching already, and it seems to be working perfectly. So I can go into my presentation then. But before I do that, I would like to introduce myself for those that have not been to a session with me before. My name is Sonja Philipp. I am an adjunct professor at the University of Göttingen in the center of Germany. Adjunct professor in Germany means that I am a professor, but I don't have a position. So I earn my living as a one-woman company named Geophil. And so what I basically do is some consulting on fracturing and related fluid flow, mainly for the geothermal industry in Germany. But I also focus on teaching, in fact, on these topics, and both offline and online now. And I also do teaching and excursion for everyday people, so normal people, not professional geologists, but on geological topics. And my excursions go to sites in Germany, but also to Iceland, for example, a country which I like very much. Yes, before I became a professor in Göttingen, I was an assistant professor because this was changed into an adjunct professorship. So I was a professor really with the students and everything, and a salary, but this was only a temporary position. But before I came to Göttingen, I was in Bergen in Norway, and I did my PhD there. And before that, I studied geology in Jena, that's in Eastern Germany. Yes, that on me. Now I see if I get any comments where you are from. Okay, there's Christina again, and Alice is watching and says, good morning. Yeah, well, good morning to you. Here it is afternoon, and Mohammed Qasim also is watching, and to him I would like to say a special thanks for inviting me to give these lectures on learning geology. I see there is quite a number of people watching already, so I think I can start with my presentation now. Today the topic is natural disasters, and there are of course many more than I will talk about, but I will focus on volcanic eruptions and earthquakes, not because others are not interesting, tsunamis and storms and landslides and many other problems, but because I can contribute only to these two types of natural disasters. And I think this is already quite a lot for this maybe half an hour that we have together now. If you have any questions, please write them into the comments. I will go into the questions at the end. And if I don't see your comment, then it can be some technical issue, because sometimes Facebook doesn't show the comments immediately, but I will go back to the comments afterwards and try to reply to them in writing. And we will also have a Q&A session next week where we can discuss also on Zoom together. I'm using the tool Zoom that allows me to share my screen, and you can still see myself also, but it's also a tool that can be used for meetings, and we can stream to Facebook there. So I will say a little bit about that in the end, that you may join me for a live discussion next Tuesday, in fact. Okay, so volcanoes, of course, you all know something about volcanoes, even if you're not a geologist. I'm pretty sure that you know something. And the typical volcano is the stratovolcano here. A very famous example is Mount Fuji in Japan. And that is kind of the picture that most people have in mind when it's about volcanoes. But there are also other volcanoes, and as many of you know, for example, the Yellowstone Park in the USA, for example, is also on top of it's inside a caldera, so a special type of volcano that is collapsed. And this is in fact a very huge caldera volcano, and there is a magma chamber that is still active below this area that can be seen easily because there are a lot of geothermal things like geysers and solfatars and so on. But there are, of course, other volcanoes like that also in the world. But these are probably the much more dangerous volcanoes than the stratovolcanoes or the shield volcanoes that we can see, really. Because roughly speaking, the longer a volcano has been quiet, the more dangerous it can be. Not always the case, but as a general rule of thumb, it holds that volcanoes that have been quiet for a long time, and in the case of the Yellowstone caldera, we are talking about roughly 600,000 years. We have geological proof or evidence that the volcano has been active several times, and 3 times in the last 2 million years. But we cannot really say from that there is it's kind of overdue now. So this is something I can go into more detail if you'd like to, but this also keeps us, well, I don't want to go into too many details here without, I don't want to keep this too long here, but just briefly, we cannot really say that the volcano is overdue because of some time between the eruptions that were in the past. But in statistics, we can say that, okay, there is a certain probability that the volcano can be active, but we will not use this only statistics for that. We usually use observations of the volcanoes. For example, we do measurements if the ground is uplifting, or if volcanic gases are coming out, and the gas composition is changing. For example, there is coming more CO2 or more sulfurous gases. And so if there is some change in the volcanic activity, it can be an indication of there will be a volcanic eruption in the near future. Also, there is seismic measurements always at volcanoes. Well, if there is a monitoring system, at least, if there are seismic, if there is seismic activity, it can be, of course, because of tectonic earthquakes. It can also have to do with human actions, but it can, of course, also be because there is magma moving in the volcano building or somewhere in the ground. And what is very typical are seismograms like this one to the left. This is a so-called volcanic tremor. That means this is a strong indication of that there is magma moving at depth. There are many things that could be said about volcanoes, but this could be a whole semester's teaching here about that. But we cannot do that, of course, here. But the one way of classifying volcanoes is the so-called volcano explosivity index. That means gives an indication of how much material is coming out of a volcano during one eruption, and how long a volcanic eruption will take, and how much is it an effusive volcano only if there is water, lava streaming out, or is it explosive volcanic eruption? That means that we have pyroclastic rocks that occur there, and this has, of course, the most destruction and the most people dying from explosive volcanoes. So such a super volcano as these large caldera volcanoes, like the Yellowstone caldera are called, can have magma volume of several thousands of cubic kilometers erupted, and a VEI of 6 or even more. Okay, when we like to understand really volcanoes, then we have to understand two things. First, we need to have magma in the ground. In the uppermost mantle, there is the rock is partly molten. We call this the asthenosphere, but this partly means about 1%, and this is usually well, it is magma in a way because it's molten rock, but this will never lead to any volcanic eruption because this is so little. But so if we have a larger accumulation of magma, we can get so-called magma reservoir if it's in the mantle, and it will, because it's lighter, has a lower density than the surrounding rock, and it can be propagating upwards. It's usually fractures that form, and the magma is going through there because it has a lower density. The buoyancy drives the magma upwards. And then we can get another magma accumulation inside the crust, and that is commonly referred to as a magma chamber. And if the dikes, so the fractures that let the magma come to the surface, really reach the surface, and the magma can come out. When the magma is reaching the surface, we call it lava then we will get volcanic eruption. But fortunately, most of the magma movement inside the mantle and crust does never lead to volcanic eruption. So most of the magma really stays in the ground and will never lead to any volcanic eruption because it cools down inside the crust or even in the mantle, and we will not get a volcanic eruption. So we need to understand what are the parameters that decide if the magma can come to the surface or not. In a homogeneous crust, we would expect, well, more or less all the fractures. As long as there is some magma overpressure, some magma pressure, we will expect that all dikes would come to the surface and lead to volcanic eruptions. We call that feeder dikes. But in fact, most of the dikes do not lead to volcanic eruptions. I forgot to translate the slide. This is a dike swarm in eastern Iceland, and on top it should be written a quantitative studies. That means that there were studies made in the field, for example, in Iceland, but also in other volcanic areas, that show that about 1/10 of the magmatic dikes, the igneous dikes, really lead to volcanic eruptions, and 90% of the dikes that are coming out from magma chambers and propagate upwards never lead to volcanic eruptions. So most dikes are in fact stopped in the crust, and what you see here already is that in this part of the tertiary crust in eastern Iceland, there is layering of lava and pyroclastic rocks, and that is very typical that the crust has some layering. Can also be sedimentary rocks, of course, that have some layering. And this layering is, of course, in grain size, for example, and composition, but the dikes as fractures don't really care about the rock type, but they care about the mechanical properties of the rock. And there, the most important one is the strength, but even more important is the Young's modulus of the rock. That is the stiffness. That means just how easily a rock can be deformed. And here is a very nice example also from Iceland of a dike on Reykjanes, that's in southwestern Iceland. And this dike, as is seen here, is inside a tuff layer, a pyroclastic layer, but it stops at the contact to a stiffer lava layer. So the tuff layer is rather soft, and the lava layer on top is very stiff, and the dike does not manage to propagate into the stiff lava layer. You can also have the opposite situation, that the softer tuff layers are stopping the dikes. That depends always on the remote stress field and some other issues. But we can also have some very complex lava or dike geometries. Here you see a dike that is coming, of course, from below, and at a layer contact, it changes into a sill. That is the German word for sill here. There is a very thin sill then following this layer contact, and again, some other place, it's changing into a dike again and propagates further upwards. So dike and sill geometries can be extremely complex in layered, or generally speaking, in heterogeneous rocks. On this topic, I myself made several series of numerical models. This is a long time ago. This was, in fact, I started this during my PhD, and I will not go into much details here. But on the left-hand side, you see magma chamber, or generally indicated as a fluid reservoir. A magma chamber is just a certain type of a fluid reservoir, because magma is, of course, a fluid. And you see here the stress field that exists in the layered crust, in a very simplified layered crust. Here the layers have the layers with A have a high stiffness, and the layers B are very soft layers. And here you see, of course, that in the stiffer layers we get higher tensile stresses. Here sigma 3 is the minimum compressive stress, or the maximum tensile stress. So these are the layers that are most easily fractures in general. The right-hand side, you see the trajectories. So that's the direction of the maximum compressive stress. This is the direction into which dike would propagate, or any extension fracture would propagate. And if you see a dike coming out from this magma chamber here, you see it would do something very similar to what we saw in this field picture earlier, that it at this contact between a softer layer and a stiffer layer here, it will either be stopped completely, or if there is still enough overpressure that it can propagate, it has to change into a sill, because it cannot propagate as a dike, because the stress trajectories are prohibiting that. Coming to earthquakes, as you probably know, earthquakes have to do with faults. Faults are parts of the crust, so we need still brittle crust, brittle deformation. That means not ductile, so folding and so on. So, but rather stiff rocks, rather hard and cool rocks in the uppermost maybe 20 kilometers of the crust. And there we have faults formed. So when the rocks are displaced against each other, this often has to do with high stresses inside the crust. mainly tectonic stresses. That means plate tectonics, for example, that the plates are torn apart or moving together or aside from each other. So we can form a fault. There are various types of fault, and we don't need to go into the details here. But what is interesting here is that there is a rough correlation between the fault displacement, that means how much the fault moves during an earthquake at depth or also at the surface, what we can see at the Earth's surface, and the length of a fault, that means its total distance on a map, and the earthquake magnitude. Magnitude is the how strong an earthquake is. There is the typical scale is called the Richter scale or the Richter magnitude scale. That means that one magnitude more is in fact roughly 31 times the energy released during earthquake. So this is a logarithmic scale. So 2 magnitudes mean roughly 1,000 times the energy. And so there is the longer a fault, the higher the displacement during an earthquake that is possible, and the higher the displacement, the larger is the earthquake magnitude. The strongest earthquakes that have been measured on Earth were the strongest of all times was in 1960 in La Divia in Chile. And I think the second largest was in 2004, the great Sumatra earthquake. They were about 9.23 something. And they were both on faults that were 1,000 kilometers long, and the total maximum displacement was 20 meters, roughly that. And that is a very large fault. That means if you don't have such a large fault in a certain area, you will not be able to generate such a large earthquake. For example, we in Central Europe, we don't need to be afraid of such large earthquakes because we simply have no such long faults. It's also that these strong earthquakes really can occur only in compressive stress regimes, like in subduction zones and so on. So there is always a correlation between earthquake magnitude and fault displacement and length. And this we can also use to predict the earthquake risk in a certain area. If we have no large faults, we will not get a very strong earthquake. And this is also very important when we talk about stimulating fluid reservoirs, for example, for geothermal energy production, or also in shale gas reservoirs, for example. Because there's always a discussion then that, of course, the hydraulic fracturing can induce earthquakes. And this is in fact why we do that. We want to create fractures, or we want to have existing fractures displaced. We want them to move to generate permeability. But of course, we don't want to have very strong earthquakes that lead to great destruction. So, but we can always be, so before we do this hydraulic fracturing, we should always try to find information on existing faults, because if we have active or potentially active larger faults, that means not only the size of the fault, but also its orientation in the current stress field that says if the fault can be active or not. If we have this information that there are potentially active faults, and we should be very careful with any hydraulic stimulation, because then we can, of course, use earthquakes. But if we have no large faults in an area, we will not be able to create any large earthquakes. So in case there is no natural earthquake activity, we cannot really induce any earthquakes. So what is not, it's not technically possible to create a large earthquake if there is no natural earthquake possible in a certain area. One last part on faults that is not it's more a positive aspect in a way of faults, is that fault zones also have a hydromechanical importance. Just very briefly, a fault zone typically consists of a fault core, that is the innermost part, that is the part that is actually slipping, is moving, and this fault core typically consists of fracture or fault grout and has a very low permeability, and the outermost part of the fault zone is then the so-called damage zone. That is the part where we have a lot of fractures and increased permeability typically. But this also has to do with the current stress field of the area. So if the fault can be active, it can be of great importance also for the hydraulics of an area. I'd like to show you two examples here. In the lower part, you see a large fault zone in northern Norway, where after an earthquake of magnitude 4, there was water coming out, pouring out from the fault. This was a reverse fault, and on the picture on the upper part you see a fault, or you don't see actually the fault zone, but there were two earthquakes of magnitude 6.6 in Iceland in the year 2000, and the geothermal industry was very happy after that, because the yield of many springs or wells increased enormously, and they could use this additional hot water that was transported to the wells. Some of the wells even became artesian. That of course creates new problems, but as you see on this picture, but in generally the activity of the fault can be positive for hydraulics of a geothermal area, but this always has to be taken into account, because this also can create, of course, new problems. So earthquakes have always to be considered for any fluid movement inside the earth crust. So briefly about what is important for geologists about volcanoes and earthquakes, when it's also about the future of these fields. Of course, what we are doing is that we map out the structures, the fault zones, for example, what we can see in the field, or in with remote sensing, for example, for larger fault zones. And we map out the volcanoes, of course. We do observations. We make measurements, if possible, of the ground deformation, for example, or volcanic gases, for example, and also the yield of springs, for example, we can measure. And if there are any changes, we can use this information to make predictions. This is, of course, it's not a trivial task, and it's not even possible in the same way for every volcano or every earthquake area. But the predictions are improving, and in some volcanic systems, the predictions are quite reliable. And one thing is, then we can also try to mitigate the risks. That means that if we know that there are dangerous volcanoes in an area, or there is a high risk of large earthquakes, and we can, of course, give advice to the authorities and improve the quality of buildings, constructions, and so on. And you all know probably about the Fukushima earthquake, and the Japan nuclear power plants are one of the best of the world, but they did not take into account an earthquake of magnitude 9 in their plans. So they were built very well, but did not expect such a strong earthquake, and that was, of course, a very big problem. And one thing that might be possible in the future, but I don't think any of us will experience that during our lifetime, is that it might be even possible to prevent some volcanic eruptions or earthquakes by, for example, inducing fluids and induce smaller earthquakes to avoid the large earthquakes. But the problem there is that we need 1,000 earthquakes of magnitude 7, which is already too large to avoid a magnitude 9 earthquake. So we rather would like to go maybe below magnitude 3 so that there is no strong destruction. And that means to avoid an earthquake of magnitude 9, we would need to have 1,000 times 1,000 times 1,000, so a billion earthquakes of magnitude 3, which is not really realistic to do that, not at the moment, of course, but it might be in future generations. This could be an interesting thing if we could place the earthquakes at the correct points to avoid very large and destructive earthquakes. And similarly in volcanoes, it might be an idea to try to release the magma pressure and avoid the destructive eruptions and have rather smaller eruptions at many places, or cool down the magma in the ground and avoid the volcanic eruption totally. As I said, these are just ideas for the far future, not in the near future, definitely not. So now I will check for the questions that you have and the comments that you made. If you have further questions or comments, please write them in the comment section. I'm also happy if you have really new ideas or other ideas than I pointed out on these topics. I try to comment on them, but maybe it's also some aspects that I didn't think of. So I'm very happy that we can have an interaction here and some kind of discussion. But in fact, I would like, before I go into the questions and comments now, I would also like to invite you for next Tuesday. We had this Geology for the Future series this week. I gave a talk every day on various topics, and on one day we started a discussion live with me on the Zoom tool, but this gave us the idea to add here one more live session where we'll only meet for discussions. That will be taking part on Tuesday, same time. So it's 5 p.m. Central European and different time, of course, in your place maybe. And we will have time there for questions and answers and some discussion using the live tool so that we can just discuss in person as well. But you can also just write your comments in the chat, of course. You don't need to be live with your microphone and camera with me into Zoom. It's up to the participants always, of course. You can also just watch and don't need to write anything. Okay, then I go into the comments now and see if there are any. Yes, there are. Okay. I see that several are saying hello again. You're from the US, from Florida. Barbara also says good morning. Cyril says good evening. I'm Mumea from Nigeria, a graduate geologist. Very nice, Cyril. Victor again is watching. Thor is watching again. It might happen in 1883. The Krakatau in Indonesia can release the loudest explosion to reach in Perth and Mauritius. Yes, in fact, the Krakatau eruption is a very famous one that was heard in very many places, very far away, and also had effects on the local climate in many places around the Earth. In fact, that's a very important eruption there. Thor also says in geophysics, the Snell's law can apply for seismic waves. Yes, I guess so. Sorry, I am not familiar with Snell's law. I'm not a geophysicist myself. I have some basic education in geophysics, of course, and I work together with geophysicists occasionally, but I'm not familiar with the Snell's law. Sorry, I cannot comment on that. But so if you would like to add to that, you can of course do that. Otherwise, we can also discuss this maybe on Tuesday. And Cindy says just thank you. I thank you, and I thank all the others. So I wait for a moment here if there are coming any more comments, because there's always also a time lag until you see what I'm talking about. There is some, so it's delayed. So I continue here a little bit to wait for more comments if there are any. If there are no comments now, you can also, of course, add your comment later on. And if I did not see your comment in case, well, I read all that there are there, but sometimes Facebook doesn't show them. I will come back to answer the comments later on. There is one more comment by Victor coming in. Guten Tag, hello. So before trying to apply hydraulic fractures, do we need to study the geomechanics of the rock? Yes, definitely. So we should always know the geomechanical properties of the rock, and not only the properties, we also need to have information on the geometry of the layers that we are going to fracture. So there is always an intensive study of the local geometry and geomechanics of the rock before hydraulic fracturing campaign is planned and induced. And Danny says, first, I would like to say thanks for sharing your job with us. Thank you, and I really enjoyed your conference. Thank you very much. You say first. If you say second, then there is maybe coming a question from you. So I wait once more if there are any more comments. If you watch the replay, you can of course also add your comments or questions afterwards. So Benjamin says, hi from Bolivia. Can you talk about sliding structures, please? You mean landslides? Probably. Well, I have not prepared anything about this. Maybe we can discuss this on Tuesday a little bit. This goes quite far away from the topic of today's lecture. Of course, landslides are a great problem, and landslides have to do with the structure of an area, and also with can be induced by earthquakes as well. Of course, also the volcanic buildings can have also induce landslides on their mountain hills. But well, I don't know, a very general lecture on landslides I don't think is feasible here. If you have any specific questions, we can maybe try to answer them here, but a general lecture is not thought of yet now. And Victor just says, thank you so much. Yeah, I thank you also. Thanks also that you wrote this comment here. I'm happy that many people joined, and I got many questions and comments. And I say goodbye to you now. If you're still writing comments, I will answer them later, and maybe we see each other again on Tuesday. Have a nice evening and take care. Bye-bye.